So I guess I'm fairly well qualified for the Schmidt Falkor thing because I've been on 3 cruises on their ships, fairly long ones, and have a fourth one coming up. Well, actually it got postponed, but that'll be down the road a bit. Before we get started, I'd like to point out I was just talking with Gina over there, who's a teacher at Iolani School, and she was actually on one of the cruises that I'll be talking about earlier this year, and some of her students are there with Debbie, another teacher there, and they made these models of some of the seamounts that I'll be talking about. So after the talk, when the lights come back up, you can go over and take a look at some of the models, and she made these lesson plans that the students were able to take and learn from. Some real kind of hands-on work. And during the cruise, they were doing a kind of a telepresence, remote satellite call to the classes as well. All right, so to get started on the talk, I'd like to give a little credit to my technician and junior colleague, Jonathan Tree, who's was on a lot of these cruises with me and took the lead on some of the interpretive mapping that you'll see this evening. So to start out with kind of the wide view of all the big Pacific, one thing I like about this view is that just shows how big the Pacific Ocean is, how far things are spread around, and really there's no continents in view except for a little bit of Australia down there in the left corner. So all the monuments, of course, up here, Hawaii and the northwestern Hawaiian Islands, the Papahanaumokuakea Marine Monument. In the central part, you have the Pacific Remote Islands Marine National Monument, made up of all these islands spread out, Wake, Johnston Atoll, which I'll be talking about some tonight, Kingman Reef, Palmyra, Jarvis Island down here near the equator, Howland and Baker Islands. Howland's known for one of the potential, where Amelia Earhart was supposed to land and was lost on the way there. And then Rose Atoll Marine Monument down here on the bottom. It's part of American Samoa. And then over to the left, to the west, Mariana Trench Marine Monument. So there's been a lot of work in the past. Well, a lot of us, and a lot of people before us, have been working in these areas for various reasons for many years, decades. But in the last maybe 3, especially 3, but say 3 to 5 years, there's been a big push to study these marine monuments in more detail and with more assets or more ships and vehicles and things. And part of that's driven by them becoming actually monuments in the past 10 years or so. And also they've been expanded just in the past year or 2 or 3 years, depending which monument it is. So their area has been greatly expanded. And actually this map is out of date. This is actually from Google Earth, still showing some of the old, the original boundaries. These squares are 50 miles on a side. But go down to the next view. These are actually the expanded boundaries. Green's a little bit light, sorry about that in here. The northwestern Hawaiian Islands, Papahanaumokuakea Monument expanded to the 200 miles on a side, 400 miles wide. The Johnston Atoll Monument has also been expanded in the past few years to a full exclusive economic zone size. And then Wake Island, and then some of these down here are Jarvis. Some of these aren't, the ones that are black are just the political boundaries, but they haven't actually been expanded yet. And so I'll be talking about, there's been work done in all of these, but there's basically 8 of these to talk about. So I'm only going to really focus on these 2 that I've been on with cruises recently, the Johnston Atoll and northwestern Hawaiian Islands for this evening. Now this is kind of the end result. I'll just show it to you now of one of the areas. This is the upper northwestern Hawaiian Islands in this magenta purple box here. This is the location of it. It's all isolated seamounts. Some of the ones, you probably can't read these labels, but these are Midway Atoll, Kure Atoll, Pearl and Hermes Reef, so they're familiar. And the rest of these are other seamounts that either reached the surface in the past but are sunk now or never did reach the surface. So this is kind of our mapping overlaid on a kind of a Google Earth level quality map, so you can see the difference, hopefully, in the detail that you can acquire. Of course, this requires a lot of ship time going back and forth in a ship like Falkor or something similar. So maybe zoom in a little bit to convince you that we need to do this. Why more mapping? So this is a Google Earth image of a couple seamounts pass of a modern seafloor mapping system that's kind of rumply texture. This is just kind of the typical resolution you see when you zoom in on a Google Earth map. Now this is the kind of resolution you get from Falkor, or another ship with a modern multi-beam system, we call it, multi-beam sonar system. Basically, high resolution you emit a fan of sound, basically consisting of numerous data points that generates a number of hundreds of data points, depth points per ping, and you go back and forth across on the sea surface, mapping the sea floor. These black lines are to represent what the ship track would be on the bottom. So we call this mowing the lawn, back and forth, just like when you mow the lawn, you overlap a little bit. Miss anything, so we overlap some of the data, so we get a continuous map and data set of the seafloor. They do this by beamforming, acoustic beamforming, to generate this very focused swath of sound. Something like other types of electromagnetic signals, say, or as simple as a flashlight. If you have like a mag light and you dial the bezel down, you can focus the beam by just using lenses. So we're using acoustic lenses in these systems. They're very complicated. I don't fully understand the details of how they work. I just like to use them and generate a lot of data. That was the ship. This is actually my colleague Chris Kelly, who was the lead on a couple of these cruises. This is what it looks like in the control room. It's a little dark, but we keep it dark. We have a lot of displays, a lot of computers, a lot of feeds coming in. We help. This one display where you see over here with this kind of pattern here. This is the actual real-time data coming in from one pass with the ship. With the with the bridge crew, who has similar displays, and we help. We ask them to go certain ways, and they accommodate. They drive the ship so that we don't miss any coverage. Quality of the data coming in, and we're always planning kind of for the next line or the road. So besides kind of natural features like seamounts and all kind of mid-ocean ridges, this technology can be used for searching for man-made objects. So we have a airplane that's imaged here in one of these high-resolution systems, and of course a shipwreck down here. This multi-beam sonar and other similar side-scan sonars are used for searching for downed jetliners like the Malaysian airliner in the Indian Ocean, and other ones, say, off of the Air France one years ago off of South America. So you can use applications. Again, we use more for studying geological features, and this is a representation of one swath of we call seafloor topography bathymetry, and so this is one pass over a seamount. We use false color. We use lighter colors typically to represent shallower areas, and the darker colors, like the blues there, to represent deeper areas. It's kind of a mind thing to help your brain figure out what's up and what's down. And then below, which is takes a little bit of getting used to look at, is these systems also generate data or side scan, backscatter data, and that's kind of like a aerial photograph, only using sound for the seafloor. So it gives you an idea how strong the acoustic or the sound return is, how strong it is. So you can kind of tell whether it's sediment or rock or a steep slope or a gentle slope. And so using these two together is very powerful and helps us with interpretations quite a bit. So the first cruise I'll talk about is over New Year's this past year, and we finished in mid-January. That's the one that I mentioned Gina was on, and we had the opportunity with the Mid-Ocean Institute to write a proposal to get on what they called a trans-ruse or a transit cruise. And what the idea was that they were working in the Western Pacific off Guam testing their new ROV. And then they wanted to reposition the ship to Hawaii and the west coast of the United States. So they offered, rather than just driving across the ocean and not doing anything transiting there, they offered an opportunity to do some science along the way. So that's why we had a project at Johnston Atoll. It was kind of right on the route. They didn't really have to divert much. It had recently been expanded, and we wanted to map some seamounts in the new expanded area. The only unfortunate part is that we had to fly all the way to Guam to come back to Hawaii, and the transit from Guam to Johnston Atoll was 10 days, pretty much right into the winter trade winds, and it was a bouncy ride for a while. That's one reason we diverted down through the Marshalls, to kind of get out of the strongest trades, and then came back up when we had to. So that was our cruise plan. And oops, sorry, wrong way. So this is kind of a blow up of the Johnston Atoll unit portion of this Pacific Remote Islands area. So this circle is 200 nautical mile radius, centered on the actual Johnston Atoll. And it's a 400 diameter mile wide circle. And the square, as I had mentioned before on the other map, this was the original protected area, 50 mile square, centered around the atoll too. So when they expanded the monument, I think it was 2014 in this case, it went basically to four times the area as it was previously. So a lot of features. You can see all these seamounts in the this is the low resolution, kind of the Google Earth type of quality data that I showed you earlier close in. All these, say 30 some seamounts in this South Johnston became under the protection of this new boundary. So it was kind of some leverage we could use to write a proposal, and they say, yeah, we should go look at some more of these. And we're in collaboration with other groups like the NOAA Oceanus Explorer group, who went here actually just last month and dove on some of these features. So I'm going to zoom in on, we ended up mapping about 6 or so of these seamounts down in this lower, and zoomed in here. This is the center of the protected area, the Johnston Atoll itself. We were working down in this box. The first thing we do to avoid duplication is we go to the national database that's managed by NOAA, and they collect all the high resolution data and a lot of other types of data too. But this is all the multi-beam high res data that existed in this area prior to us going there with Falkor early in the year. And we can download all that. Anybody can go and download it. It's just if you're able to use it, if you have the software and the computers and all that to be able to use it. But it's freely available to anyone. So we download it, we grid it, we put it together and make maps, and then we base our surveys on that. So this is what it looked like, zooming, kind of flipping, looking out straight down on it. This is what it looked like before we got there, and then after that. This is our completed mapping, and we were only actually on site in this case for I think about 6 days before we had to leave. So it was about a 20-day cruise, and we actually had about 6 days of 6 days of science mapping work on site. And of course, we were collecting data on to and from, but it was just a single swath as we transited across. So this is a 3D view. 3D, we make these models. We can fly through these models and also do analysis this way. These are the 6 seamounts we mapped. And then some statistics. This is the area, 11,000 square kilometers map. We actually accomplished more than we proposed in the proposal, so 1.5 times or more what we had asked, what we thought we could do. And then, so just for comparison, those areas don't really mean much to most people, so we always try to put in some kind of fun facts of how big that is. So we mapped like about the size of Connecticut. We had a guy on from Guam, so I threw that in there, 7.5 times the size of Guam, and about twice the size of Delaware and some other countries. I think we had some people on there from these places. So, So this, I just kind of want to show you the process of what we do when we do this mapping and what's involved. So I just chose one of these seamounts. We proposed this name Pierpont after the first person to describe this area. It was an American captain named Joseph Pierpont. Only he accidentally ran aground on one of the shoals there, and he described this later, but he didn't claim them or didn't name them. Maybe he was embarrassed that he ran ashore, I'm not sure. But then a few years later, a British captain by the name of Johnston came, and he actually claimed them, and so that's why it's named Johnston Atoll. But we thought we should give this guy some credit, so we propose a name of the seamount, and so far it's kind of past the initial stages. So that's, yeah.
What's the depth of that, of the top of that?
The tops are about 1,000, a little over 1,000 meters, I believe, in this case. So about over half a mile down. So the this is what I mentioned, the backscatter, the kind of the reflectivity intensity. So we can also put that on top of these models. This is the same seamount with that draped on top. Then what we do is, so on the left of the there is the bathymetry or the topography. On the right is the acoustic backscatter that I mentioned. So the way we do this, we take these data, we take the original shipboard data that comes off as it streams off, and then we wait till we're done with a feature or a portion of a feature, and we take those files and kind of grid them. We grid them to a certain level, which basically means reducing the data down so it becomes less voluminous, but you're basically putting it all together in a mosaic. And then you can make maps out of it, or make data grids, or for further analysis in software programs or geographic information systems, GIS products. So we construct the 3D models like I showed you already. And then the key part is, this is what my technician Jonathan is very good at. We're digitizing the geologic units and the structures using these morphological observations. So basically what we're doing is creating geologic maps just like on land, only we don't have the benefit of going around and walking around on an outcrop or a feature. So we're doing it kind of with remote sensing, and also sometimes ground truthing with submersibles or ROVs or samples if we can get them. But in this case, we're just doing it based on the very high resolution data, and we were able to, by doing this down to a 20-meter grid cell, which is basically is a footprint we gridded at, so something like 60 foot square, and we can resolve features of that size down at these depths, we found. Because one reason is the system on the Falkor is very high resolution, very good installation, so we were able to really push the limit of the data in that case. So it's been very productive that way. So on the left, on the bottom left, is a structural map. The radiating red lines are rift zones, or these are all extinct volcanoes, and they're in the range of a Cretaceous age of, say, 65 to 80 plus million years old. But these are, the red lines are rift zone ridges where the magma had flowed down at one point. So these are like on the east rift zone of Kilauea volcano currently, which is active. And on the right are the units, the geological units in the different colors. And a lot of the ones here are either the carbonate or the ancient coral reef top. The greens or the light greens are some of the volcanic flank, and then the landslide areas are also a different shade of green. So this is just zooming into the summit to give you a little more detail, show you a little more detail of what we do. This is all the kind of the very orange areas are this carbonate cap. So this is ancient reef material when the volcanic seamount rose up and was eroded down, and it became a flat top, or guyot, G-U-Y-O-T is what we call these flat top seamounts. So this was presumably at sea level at one point. And then sunk back down, sunk back down as the volcano subsided under the weight on the tectonic plate. Now these other roundish features, there's one right to the left of the word cones, and then one in this area, and then down here to the bottom is actually one with a little crater in it, and then some other ones over here. So this is interesting. These are volcanic cones that erupted through secondary volcanism. They erupted through the carbonate cap after that was in place. So that's kind of like what you're sitting on now, Panama Bay and Cocoa Head. So these are features that came up later and erupted through the carbonate cap. Secondary volcanism is a little strange. It's not really fully understood how and why it happens, but we have the evidence that it does. Another way we can look at this, we generate slope maps. So in this case, the dark blue areas are lower slope. The brighter colors, the brighter blues and the yellows and reds are higher slope. So this is another technique we use to when we work in the mapping, when we do the interpretations, and another way to visualize the data. And then kind of put it all together, like I showed you the geologic map before. So this is the interpretations of the structure and the geological units outlined and then labeled with all those different little three-letter designations. They all mean something related. They all mean something specific, and some are related depending on what the lettering is. And then also some of these indicate fault scarps that were probably landslide head walls. And then this is all draped on top of the topography and the acoustic backscatter, so you can get a sense of how rough the bottom is and how steep it is at the same time. So a close-up of the geologic and structural maps. This is kind of a summary of what we found on the top. So this is all these different cones. So we found that this seamount, this Pierpont seamount, is just one single volcano, although it has maybe greater than 40 individual cones that erupted through the carbonate top. All these kind of hatchered, all these hatchered circular features around. A lot of them are actually around the rim. Some are in the center. The central platform is kind of all this part in the middle is dominated by kind of low intensity sedimented areas. And then the upper edifice flanks, all the region around here has a lot of eroded surface that can be, and a lot of the submarine rift zones, as I mentioned before. So there's eroded volcanic flank. These are very old, as I mentioned, and they tend to, they are very distinctive from younger seamounts, younger volcanoes that are underwater. So this is a summary of the kind of the four of the major seamounts, and I think actually all of these are, there's little models of each of these over there on the table. This is the geology and structural maps and the geological units. We always have a key or a legend in the somewhere on the map so that you can actually tell what these different colors and these different features mean. Some of these other bigger seamounts actually have multiple volcanoes we've interpreted. So these red lines are the contacts between different volcanoes. So much like on Oahu, we have Ko'olau and we have Waianae. On the Big Island, we have 5 volcanoes. So there's a contact between that's separating the volcanoes. In the same case on these underwater mountains. So again, in total, so we have of the 6 seamounts, we figure there must be actually 8 to 10 individual volcanoes, as I kind of alluded to recently, and that they have complex eruptive histories because they're kind of tagged on to each other. And then they have secondary volcanic cones. All right, so switching to the northwestern Hawaiian Islands. Now this is a series of kind of a compilation of a lot of work I've been working on up there since the year 2000. And Janie Culp in the front row has been with us on a number of those cruises. And but the major push on the mapping of this came a few years ago in 2014. We had 2 long cruises funded by Schmidt Ocean Institute on Falkor, 2 back-to-back 36-day cruises. They actually were looking to do more work. We had been awarded 1 cruise, and then we were looking to do more work, or they were looking to make the ship busier, and they decided to ask us if we wanted to have a second cruise, which is kind of unheard of in this field of work. It doesn't happen very often. So I think most of you are probably familiar with the Papahanaumokuakea to some level, especially if you come here to these talks regularly. Again, it's been expanded just last year from the original size, which was 100 miles wide, to 400 miles wide, or 200 miles on a side from emergent land. So again, 4 times bigger than it used to be, and it's of course full of all kind of living, non-living resources, marine archaeological things, cultural things at land and at sea. So there's a lot of reasons to go there. The U.S. Geological Survey actually went there back in the mid 80s to early 90s, and this was in response to the proclamation by President Reagan in 1983 that 200 miles from the coastline of the U.S. would be sovereign territory. It used to be 12 miles, the territorial limit. So that greatly expanded the coast. So there was an initiative put forth to map all the U.S. Territories out to 200 miles. So the most efficient way, that's a huge task, even with the systems we have today. So what they did, they used a system called Gloria. It's an acronym. It's not really a very good acronym, so I won't go into it. But they used this wide swath side scan sonar system, which covered a lot of area, but it wasn't very detailed. And it didn't have any, so it just provided the acoustic backscatter. It didn't have coincident or accompanying bathymetry or topography. So it was good for large scale regional things, but not the detail that we were kind of looking for. So I just wanted to show you that. It took several years to map the northwestern Hawaiian Islands. And that was long before it was any kind of reserve or monument status. In 1994, so 23 years ago, some of their scientists published a kind of a general geologic map, which kind of looks like what I've showed you, what we've done, only this is a regional thing. And they were mainly interested in submarine landslides. So I've talked here about that in the past, but that's a whole other talk. So that's these giant submarine landslides. That was the focus of their study in their interpretations, and they only had basically 6 different units showed here, 6 different geological units. So our goal was to try to do better than that and update it, 20 years later and see what we could come up with these modern seafloor mapping systems. So on one of our cruises, we worked in the central area of the northwestern Hawaiian Islands between Lisiansky, Laison Island, and French Frigate Shoals. And then that was the above one is what was there before from the national database and other cruises that we'd been involved in, and below is what we added with Falkor during one of the cruises. And then the upper seamount area, which I showed you a map earlier, the same thing. This is the data that existed before we went up there, and then with one long cruise we were able to pretty much fill in all gaps of the major features. And then again, these are the Curie Atoll, Midway Atoll, Pearl and Hermes Reef. I wanted to show you a little detail again of one of these features, which is very interesting. It's been referred to as Bank 9. There's a number of basically unnamed banks, and people just designated them with Bank 9, Bank 10, Bank 11, or so on. Okay, so there's some of the stats when we mapped 7.5 times the area of the main islands in these 2 cruises, and basically mapped 30. This was based on the original monument size, because that's the existing size of the monument when we were up there 3 years ago. So this is a blown up image of the Gloria data from the U.S. Geological Survey of this seamount feature, Bank 9. So it's really hard to tell what's going on there, even for somebody used to looking at it. Now, if you put kind of a very low resolution synthesis of the multi-beam and background data that was available for topography or bathymetry at that time, that's basically what it looked like. So that's a little better, but not really great. So this is with the Falkor data, and you can see things are starting to jump out at you. And then you can put contour lines on it as well. It gives it a little more definition. You can actually pick them off by knowing what these contour intervals are, lines of equal depth. And then again, you can do a slope map, kind of spin it around, and you get a much better view of what's going on. So using all of this technology, we've gone from what their original, this is a cutout of that interpretation I showed you before. This is what they came up with for this one feature. And then this is what we were able to produce using the data from Falkor. And this is the same feature, and this is what we were able to do with it. And we can also make these models and these 3D models, and then drape the map on it, and then make movies. We can fly through this in real time too. But this is a rendered movie that we made. This is very useful for. We show this at our school SOS open house every couple of years. This type of thing. And we have a video wall there. That'll be in October again. I think the 3rd week of October or something. Open to the public for a Friday and a Saturday. Check your local listings. So I stepped through a couple of these features in this area. So kind of look in the central area. So Lisiansky Island, there's actually a small island here with a hypersaline lake. And then step down to, so that's, oops, sorry. That's Lisiansky, and then the next one down with the arrow, that's Morrow Reef. That's kind of an Oahu-sized feature. It's got a reef on it that's emergent during low tides, and an active reef on it still. And this large one here, this is Gardner Pinnacles. This is actually the last bit of exposed volcanic rock above the sea surface at this location. But it's mostly a carbonate or former reef top. And this feature, this Gardner Pinnacles, is actually on the order, the size of the Big Island. Basically, if you look at the underwater portion of it that used to be above water, or nearly so. And then one more feature we'll look at in detail is this St. Rogation Ridge. And that's connected to this big ridge feature. This is all underwater except for this French Frigate Shoals. You've probably heard of that. That's right in this area with Turn Island. That's a popular place for monk seals hang out there on some of those sand islands and so on. So that French Frigate Shoals is down this part, but there's this whole other underwater feature here that's pretty amazing. So this is our geologic interpretation of that area, that same area, the whole area. And then all these on the bottom is the legend for that. We have like 31 different geological units, plus we have a lot of structural units like the faults, rift zones, scarps, and so on. Now, just in the map, the focus of this project was rather than kind of pure exploration and mapping new expanded area in the Johnson Atoll area. This one is a little bit more developed because we've been working there, and I had a National Science Foundation grant to do the mapping here and also study the landslides and other volcanic features and some of the reef features as well. So the focus here and a lot of the yellow areas and the different patterns are different types of landslide deposits. The pink areas that are kind of centered around the central part of the ridge, those are the carbonate or the reef areas. And then it's probably a little hard to see, but there's these other hatchered, kind of a light green hatchered areas in between. Those are kind of other volcanic flank that we've interpreted. So kind of a mishmash of things. And you really have to zoom in to do the interpretations. This is a bathymetry or topography map of Pioneer Bank, this very steep ridge, rift zone ridge. This is the backscatter data with our units that kind of outlined. And then we turn that into the geological map. So in this case, some of the things I was talking about on the really zoomed out map, the landslide features, volcanic flank, and the carbonate areas in pink. Now these are a structural map, and all these are faults, these kind of lines with these dots, and so we can map out faults and different types of faults that we interpret, and also in conjunction with the rift zone. Moving down to the Maro Reef, again, I said this was somewhat on the order of a Oahu-sized feature. It's got a couple of big rift zones coming out to the southeast, to the right, lower right. Again, their geological map. And then in this case, see if you can see that, we also had a gravity meter aboard the ship. So it's a gravity meter, you measure the Earth's gravity field and you calculate the anomalies. So you look at anomalies in the Earth's gravity field. That tells you something about the substructure underneath the surface. So these multi-beam systems only map the surface of the seafloor. In some cases, you actually want to know what's below the what's below the seafloor. The gravity gives you some indication in a low-resolution fashion. So all these lines are actually the ship track going back and forth, and the coloration is the intensity of the gravitational, the residual or the anomaly, what's left over after we calculate out the regular part of the Earth's field. So what this tells you in the end is that the red stuff is pretty interesting because that's a higher intensity gravitational signal, and that we interpret as solidified or concentrated volcanic rocks, which you can say is probably a volcanic center or a separate volcano or part of the magma plumbing system, much like, say, currently Kilauea volcano in the East Rift Zone. So the black circles help us, we've kind of interpreted those as volcanic centers. Of course, we didn't have any data over the top of Maro Reef because it's very shallow and very treacherous, and Falkor is a fairly big ship, so we basically don't go there or can't go there. And we also can map out these terraces, all these pink lines, squiggly lines. These are different levels of different sea level stands. So they're different reef terraces, stepping, kind of like stair steps going up and down. And so we use these. You can help get the subsidence history, or how the feature sank, the Hawaiian Ridge sank, the seamount sank, and also different levels of different stands of the sea over time. And those are just mapped out with using the bathymetry and the backscatter and the slope maps, as like I showed you close-ups of before. Moving over to the Gardner Pinnacles, this is the one that I said was on the order of the size of the Big Island. So these are big areas of landslide features. The one over here is like a big debris avalanche or maybe a catastrophic submarine landslide. The one over here without the pattern is, we've interpreted as a slumping event, more of an intact failure. These probably didn't occur at the same time. This is kind of this big slumping event over here would be similar to what's off the west side of Oahu, off the Waianae side on the seafloor, or the Kilauea south flank to the southeast of the Big Island. And then this other one, this debris avalanche, should be something like the big landslide off of Nu'uanupali on the windward side of Oahu. This is our backscatter, and then we call this hummocky topography. This is kind of a giveaway to this this debris avalanche type of deposit. It's kind of a bumpy or hummocky, like I said, topography. The one over here is a more intact look to it, but contorted, just the same. And we'll use some variety of methods to determine that. And then kind of together with the geological key or legend completes the rest of it. And then moving one more example, this big rift zone ridge that I mentioned, that's part of the French Frigate Shoals area. Again, on the left is our topography or bathymetry. This feature is about 100 kilometers long, about 60 miles long. It's a huge feature, similar to the size of on east of Haleakala. There's a huge rift zone that goes into the ocean and off to the east. So this is of similar size, and the backscatter and the geological units on the right. And then kind of putting it together, you can see now with the gravity data, we had good gravity data on this, kind of the booming red signal, which indicates a strong former magma plumbing system. And then on the right are geological units with a carbonate cap on top of all this. and some landslides to the side, sedimented area, this purple area to the left in between this feature and the Gardner Pinnacles that I just showed you. So just as a final example of what we've gone through from this, this kind of crude interpretation I showed you that was done 23 years ago to what we're able to do with the same type of on the same feature. This is the east part of the French Frigate Shoals Riff Ridge area, and just kind of a picture worth 1,000 words of the detail that we can pull out using these modern systems like Falkor has. So you might be asking why we keep doing this. Sometimes when we're out there, we wonder too. So I'm kind of skipping over a lot of the basic science that we're getting out of this. I mentioned something about the landslides, and also skipping over some of the just doing it for exploration kind of thing to expand our knowledge of these monuments and what's protected in them. We don't, there's not really, there hasn't been work in a lot of these. None of these seamounts in the case of the Johnson Atoll area on the southern end had really been studied. So those are some of the reasons there, but there are living things that are down there. And these are actual examples of creatures, and all the way from crazy looking toadfish to deep sea corals, sea stars, crabs. These are all pictures, images that are actually collected from some of these marine monuments like Johnson Atoll area and the northwestern Hawaiian Islands. So there's plenty of stuff, and this is being cataloged actively by the NOAA group, the Ocean Exploration Research Group that's operating the Okeanos Explorer in conjunction with people at the University of Hawaii, such as my colleague Chris Kelly is kind of leading he's a biologist, and he's kind of leading that charge. So a lot of these creatures actually live, of course, they're the ones I just showed you are bottom dwellers, so they live on the rock, whether it's carbonate or basalt, or in this case, what's down there is a lot of these things are very old. These seamounts, as I mentioned, they're many tens of millions of years old. There's this this cobalt-rich manganese crust, or we call it polymetallic crust, that precipitates out of seawater. It grows at millimeters per million years, and it just builds up. So on the lower right, there's an example of this manganese crust. This is like about 4 centimeters, or just over an inch and a half thick, on top of a phosphorite deposit. So this stuff grows or precipitates all over the seafloor, coats the seamounts. It looks like a chocolate coating. It's kind of bumpy, actually, and it's somewhat toxic. I mean, you wouldn't want to go and lick it, but it's kind of interesting. We've been doing studies on does it affect the animals? Why do they like it, or are they have any aversion to it? I don't think we've come up with anything specific about it, but the one thing is that these areas are being looked at for marine mining, submarine mining, and eventually it will likely happen. It's just a matter of coming up with the technology to do it effectively, and also the price of minerals and metals and how that fluctuates. So they, of course, wouldn't do it in the protected areas, but there's plenty of seamounts that are that are on the high seas that are unprotected. And so what we're doing here is kind of the collaborative or the collective effort is to get an assessment, keep ahead of it, try to find out what is down there biologically and what areas may be okay to mine, and kind of model it so that you can advise on it. But before now, there really hasn't been a lot of detailed work to come to that conclusion. So I showed you this map before. Now we have a red line on here. This is what's called the prime crust zone, and that is kind of a somewhat of an empirical or and theoretical, based on oceanographic parameters. Where the seamounts that have this valuable crust would be. So this red line kind of circles the whole central Pacific from east to west, and you can see a lot of the areas in the main Hawaiian Islands to the upper right, and a bit of the northwestern Hawaiian Islands. I'll be showing you something from the Musician Seamounts, which is right here, where I'm headed to next week. And some of the Johnson Atoll is completely within it. Some of these others, like Jarvis are right out of it. And then some of the edge of the Marianas are over here, and Wake Island is within it. And there's plenty of, some of these seamount groups belong or are territories of other countries that they're not designated here. So, besides the individual pictures of biology, we find these dense biological communities composed of all kinds of things, the deep sea corals, sponges, other kinds of creatures. Not as many fish. There are fish down there, but sea stars and other echinoderms. So these are machines that actually have been built or are being built to mine polymetallic sulfides in the Western Pacific off of Papua New Guinea. So that's like hydrothermal venting, fossil hydrothermal venting, where they produce these sulfide deposits, which are valuable minerals of a different type. But these are actually the types of proposed machines that would go down there and actually extract this stuff. So it's much like strip mining on land, similar type of technology, only it's all designed to be used underwater. So you can imagine that these would do some damage down there. And I mentioned the Okeanos Explorer and the NOAA program. They're working in collaboration to some level with the Schmidt Ocean Institute and the Falkor group. So we kind of overlap. We try not to, try not to duplicate data collection. So they have been out there. They were actually out. They used our maps in last month in July to dive on features in the Johnson Atoll monument. And they are finishing up this 3-year project in the Pacific that's studying all the marine monuments. They've been to each one at least once, or actually probably at least a couple times, doing mapping and ROV dives. And I am actually headed out with them next week for 25 days to the Musician Seamounts. And what's different about that one is that most of it is on the high seas, so it's not in a marine protected area. So theoretically, the ones in the upper area beyond the United States boundary up in this area could be mined eventually. So we'll be doing ROV dives on there and doing some more mapping as well. All right, you can follow us. They have a live feed. This is probably, you're not going to remember this link, but if you just if you're interested, you can Google for something like Musician Seamounts Cruise, or if you can remember EX 1708, that's their Okeanos Explorer. That's the abbreviation for the ship, cruise number 1708. And they'll have daily dives that are broadcast from the ROV on the internet. And it's live commentary. All right, this is a super selfie off of Falkor. I don't usually show those, but that one was kind of one in a lifetime. All right, thank you. If you have any questions. Sure.
You had a big picture that showed several of Seamounts again. Several of the
From the Johnson Atoll area, or in the...
Actually, there was a string of Seamounts from Samoa going up toward Wake Island. Does that have a name?
Is it
Going from Samoa northwest.
like this one or this? Which map?
Let's see what the light's got.
Oh,
But here you got Samoa here,
yeah.
and going through the EN and Monumental, through the FY and Pacific, going up toward the...
That is up in this area?
Yeah.
Let's see. I was going to say that Tokelau. That Tokelau is over here, I think. That's, I'm not sure offhand from this angle. Yeah, sorry, I can't tell from
Anyway,
here.
the second part of the question is, going back to mining, back in the 70s and the 80s, there were sample dredgings for nodules.
Right.
And looking at the gold content, things like that. Now you show these machines, what's the estimated time that someone's going to go out and use them? And what countries are going to be doing it?
So a lot of countries, except the United States currently, because we're not part of the international agreement. But so the Japanese, Germans, Koreans, I think that those actually, they've all chartered our ships to actually do environmental and resource assessment studies and some kind of engineering studies of the seabed, like the muds. We're not doing any mining or anything like that. So they've actually had an interest in the nodule areas, not the crusts. But so those countries, and then there's a number of other ones like Belgium, I think too. There's lease blocks that have been acquired that's administered through the International Seabed Authority. So it's much like oil lease blocks in the Gulf of Mexico or anywhere else. So a lot of countries are interested, and they're actually doing the preliminary studies that are required now to do the mining. It just kind of depends on.
Studies been made about doing it safely, so all the crap doesn't end up going all over.
Yeah, that's the problem, because you have all the stuff coming up, and then you're putting it down somewhere else. So that's also water, like maybe tailings of minerals or things that you don't want. So they're doing all kinds of, they go out and do studies besides sampling the seafloor. They actually do water column studies, and they look at the properties of the water. They look at the sediments or the organic matter that rains down. They look at the plankton that's in the water column. So they'd have to do all these baseline studies, and I believe they're required to continue. If they ever did start mining, and when they do, they would have to do these studies as the procedure continues, as the mining continues. Yes?
I have two questions. The first question has to do with those red lines, for instance, along that, we would call it a rift near French Frigate Shoals. The
Right.
red lines indicating higher gravity signature, whatever it's called. Would those be what we frequently call dikes, where magma comes up and it's squeezed into pre-existing cracks, if you will, and so it's very dense? Would those be dikes?
Yeah, and that they would be in most cases. Once, the magma comes up and solidifies, and so that would be a concentration of
Very
dikes.
dense and so high gravitation.
Right. So like over Kailua area on Oahu is the kind of the central area of the Ko'olau volcano, and there's a lot of dikes over there. In the core you can see them. So that would have a high gravitational signature there. Same type of thing.
The other question has to do with Johnston Atoll data that you folks have gotten. I was really intrigued by the fact that you have these EOs, the topped off volcano seamounts.
Right.
About 1,000 meters down. So at some point in the distant past, they were volcanoes above the ocean, and they got eroded down and became flat top seamounts. But I don't think I've ever seen any evidence of one of those, an EO, presumably at sea level surface, having secondary eruption, a secondary volcanism. Right here, Hanauma Bay is secondary eruption, but it's at a much younger stage of the volcanic deterioration, if you will. But
Right.
EO is way old, so for there to be secondary volcanic eruption at that stage is amazing. I mean, I didn't see it at Pearl and Hermes or some of the Northwest Hawaiian Island EO.
Yeah. Well, that upper area, I don't probably not on Pearl and Hermes, but the other a lot of those other features in that upper seamount area, we didn't expect to find them, but and they hadn't been documented really before, but we found a lot of those flat top features up there. So those are, but what most likely happens is the secondary volcanism is probably on the same time difference scale as, like, say, here on Hanauma Bay, but after the primary volcanism, but it's just preserved for all those millions of years later.
It's preserved even though the seamount is eroded away and flat top.
Yeah, because those would have come up later, but it's still very old. But it's and part of it is maybe that now we're able to resolve these features much more than anybody has been before. So we're seeing things that were probably on other seamounts that other people mapped, but they didn't have the same quality of data.
Maybe
So-
one last question.
Sure.
The Hawaiian archipelago, the Hawaiian Islands, classic textbook case for movement of the plate over a hotspot, the formation of the volcanic islands. Johnston Atoll, I see all these volcanoes, right? All volcano islands sort of polka dotted all around. They're not all lined up. So
Right.
where do they form? I'm thinking East Pacific Rise, or is there some hot spot that sort of works up stuff in all different directions?
Well, that's actually one of the million-dollar questions of that area. It's kind of a confusing area, and partly it's confusing because there hasn't been a lot of work there. So it's part of the Line Islands chain, and that stretches down from the, say, like Jarvis Island, which I had mentioned, up through the Palmyra, Kingman, and then through the Kiribati, like Christmas Island, and those, and then up to pretty much Johnston Atoll area is probably the end of it, the northern end of it. And so it's there's been a few studies on it, whether it's a hotspot chain or not. Is, you know, the dates that are available aren't real clear on that because there's probably not enough dates. So the Okeanos was there and collected a number of rocks on their study. So we're hoping to get enough people that study that and do the dating to, you know, this just adds to the, you know, the database. So it's not figured out yet, really.
Thinner over there, which mean volcanoes become more randomly?
I think it might be a little thicker there because it's older than, say, you know, some other areas to the east. But they're, you know, it might be that they're a combination of some hotspot trace and things that are formed like off axis from mid-ocean ridges like the East Pacific Rise.
Stay tuned.
Okay. One more?
I have a question.
Okay.
In your opinion, how far are we away from real heavy commercial loading? Like somebody finds gold instead of all the countries going to go? Where do you see it happening?
So the polymetallic sulfide mining is probably going to happen just depending on the price of the material of the metals. There's a couple companies, Nautilus Minerals, and there was another one. They've you know, built these vehicles, and they were building a big ship to do it. So that could happen anytime, and that is within the exclusive economic zone of Papua New Guinea. So they're not subject to the International Seabed Authority rules. They can kind of do what they want, and so they've gone into collaboration with them. And that's a little bit shallower. That's, I think, more in the order of 1,000, maybe 1,500 meters deep. So the areas that we're kind of talking about are on these crusts and nodules are thousands of meters, many thousands of meters deep. So that's one complicating factor. I think it, you know, maybe potentially as early as, you know, 20 years down the road for that type of mining, but maybe longer, depending on who you talk to.
We're getting closer.
Yeah, getting closer. And so there's more of a concern to find out what's there in, you know, biologically before it gets kind of wiped out.